Okay, so let us start. So last class we learned about LU decomposition method. But the main question is why we learned LU decomposition method even if you had learned the Gauss elimination and Gauss Jordan method to solve Ax equals to B. That should be another question for you, right? So the answer to this question is lies here. Think of this solving system of linear equations of the form Ax equal to B. Okay, then I am asking you if every time there will be problems in real world problems, you have to optimize your solution. That means optimize the value of x, optimize the vector x, so that this gets satisfied, Ax equals to B. I told you, you have to optimize your situation in the sense that think of a traffic problem. Think of a traffic problem or your money. How many of groceries X you have to buy so that money B is satisfied? You have fixed amount of money. You can only rupees. And depending on that, how many tomatoes, how many potatoes, and how many kgs of chicken you can buy is limited, isn't it? So if your boss is happy with you the next day and he incremented your salary, so your new salary is B1, then I'm asking you that of course X will change, isn't it? Of course X will change. Yes, but somehow the price of the potato and tomato is still the same. The price of tomato and potato is still the same, which is the coefficient matrix. So therefore, I am asking you, then you have now new system of equation, Ax equal to B1. But here you see what have changed. What has changed? X will change, B1 has changed, but A has not changed. A has not changed. Even though A has not changed, for this one, you have to convert A to an upper triangular matrix, upper triangular by Gauss elimination method. Yes. Again, when I gave you this B1 vector, again you have to convert the same matrix, different upper triangular. This will be a different one because the B1 is now new. The B1 is new. So upper triangular matrix will be different. So the method of Gauss elimination will be different. The way you do the elimination step. Yes. So can you understand? It is getting so much inefficient. It is getting so much inefficient. Why? Because every time the vector B changes into different vectors, you have to solve every time the matrix A into an upper triangular matrix, a new upper triangular matrix, depending on Gauss elimination. Can you see the disadvantage here? Every time you have to convert the matrix A into an upper triangular matrix by row operations. Yes. Now, take the other case. Now, take the example of LU decomposition. Take the example of LU decomposition. So, Ax equals to B. X equals to B. Okay. If you have Ax equals to B, yes, A in terms of L and U. Now, LUX equals to B. Now, if I tell you, in this case, now the vector keep on changing, B1, B2, B3, so on. Do you think L and U will change? Do you think L and U will change? No, it will stay the same because A is not changing and you have kept A to be L into U. So here you see, previous method by using Gauss elimination, you have to do the elimination for every matrix A. Again and again, every time your vector B changes. Yes, but in the case of LU decomposition, even if your vectors B changes like B1, B2, B3, and B4, the A matrix still remains the same, and you have already decomposed the matrix A into L and U. So now you just have to solve the equations and get the answer. So you can see how drastically the number of steps has reduced if you use LU decomposition. So now how many of you did not understand? So I hope you get a feel. You got to feel what is going on here. Last bench. You got to feel what is happening here. What is happening here? And you have to speak up. You have to speak up. And louder voice. Louder voice when you play cricket. Huh? Once more. Okay. This is the last. 3 times I have explained. Okay. Okay. Let us do some drawings so that you can understand it better. Okay. Or no? So we are talking about two cases here. We are talking about two cases here. What are the two cases? The two cases are, I am telling you, you solve Ax equals to B. You know, you can solve X equal to B via Gauss elimination. Tell you decomposition also. So I am giving you a real world scenario that if you have Ax equals to B, okay, fine. Think A to be the prices of your groceries. If tomorrow tomato price kg is 20 rupees, tomorrow also it will likely be 20 unless the weather changes. Yes. So therefore, A matrix will be the same. But depending on your salary, which is the vector B, you can buy the kg. The number of kgs will be different, isn't it? So suppose I am telling B is one like a vector of 1000, all this vector, fine. Today, the salary. Tomorrow's salary might be incremented 1500 something. So I'm telling the prices of tomato is still the same. That means A matrix is still the same. X1 will be different. The kg of tomatoes, kg of chicken you buy will be different. So what is changing here? What is changing is X and B changing. But what is not changing here? A. Yes. But okay, let us solve these two by Gauss elimination. Let us solve the first one. If you solve the first one by Gauss elimination, first one, so you have to convert A into an upper triangular matrix. Upper triangular matrix. Yes, UTM, upper triangular matrix by Gauss elimination. X1 equal to B1. Yes. Now again, you have to solve by Gauss elimination matrix, convert the matrix A into a new upper triangular matrix. It will be a new upper triangular matrix. Why? Because your B1 has changed. So therefore, the row operations will change. Okay. So you will have another matrix G. So every time the matrix will change, new row operations, which is quite inefficient. Because why it is inefficient is the matrix A is staying the same. But even if it is staying the same, you have to action again and again on A. Yes. Now, you know this situation. Now let us see the situation of LU decomposition. What happens? Let us come back here. So you have LU decomposition, Ax equal to B. In LU decomposition, you decompose the matrix A into L and U. So LU X equal to B. Yes. Now here, I give you two solutions again. Your salary has increased again. LU of X1. So these are the two problems. What do you think happens? In first problem, into LU. So no operations is done. Just solve the equation. Then come to matrix, new matrix, LU X1 equal to B1. Here also, you don't have to do any. A matrix is still the same, which is decomposed into LU. So just solve the equation. But here you are converting matrix A using row operation. Okay. So here you can see how drastically the LU decomposition is efficient than the Gauss elimination. Okay. So this can be something important. This can be something important and you can expect. Okay. Fine. So this is what plus. Okay. All right. Okay. So we have discussed, we have learned about the two iterative methods, that is two direct methods, that is LU decomposition, Gauss elimination, and Gauss Jordan. Yes, we, how you can use solve this Ax equal to B using dot solve, LIANLG dot solve function. Second, inverse function, x equal to A inverse B. Third, LU function, LU of A. Yes, any other method? Tell me. Okay, I remember these three. Okay, so let us be back. Okay, now we will learn how to use iterative methods to solve, uh, the system of linear equations. Now you should again ask me, why, after learning so many direct methods, we are still learning iterative methods? The answer is the direct methods you learned in the last class. You were able to do it in class in your notebooks because these are perceivable to you. That means these are only three equations or three unknowns. But you can expect when you solve a real world problem, there will be 1000 unknowns and 1000 equations. So there, in those cases, you need iterative solvers. And your direct methods don't work nicely in case of sparse matrices, matrices which has a lot of zeros. You saw in the last class that tiny quantity in the coefficient, how it was making your system of equations ill-conditioned, isn't it? If it was in the first row, 3 into 10 to the power minus 4 example we have taken last class, what I did, I took two examples. First example, the first row was having 3 into 10 to the power minus 4. Okay, there we saw tiny differences were giving you huge. Yes. Now, the second case I told you, what you do, just swap the equations. Just swap the equations. There you see that the results was consistent. So therefore, in case of sparse matrices, direct methods will fail. High chances of failing. Okay. So therefore, you need iterative methods to do. That's the main reason. So there are two kinds of iterative methods to solve. One is known as Gauss Seidel method. Is the Jacobi method. Hmm? So yes, so there are two different iterative methods we will go through in this class. Okay, so one is Gauss Seidel and one is Jacobi method, and you will see that similar to each other. They are very similar to each other. Okay, how they are very similar to each other we will see in this class. Okay, so you know that this system of equation is just this system of equation where I have it. Yeah, yes, it is just this system of equation. Agree? Agree? This system we just wrote in matrix form. This system of equation we just wrote it down in matrix form. Ax equal to b. Okay. Now think about that equation. Let me write it here so that there will be easier for you to understand. Okay. Yeah. Fine. Okay. So yes. So what I'm asking you here is, can from the first equation, can you give me x1 value? The idea of this method, iterative method, is as you start from an initial guess. Every numerical, so start with an initial guess, that is this vector x0. What is this x0? This one will be x1, 0. The value of x1 at step. Okay. Then x2, 0. It consists of all the solution, like in your initial guess. Okay, fine. Okay. Here you are collecting all the solution and packaging them up in a vector. How this you will learn in data analytics also. How to keep your data together. How to compress your data together. Okay. So matrix, storing them in a matrix is a perfect way. Fine. Then you apply some iterative method. Iterative method. After you apply some iterative method, you go on to this new solution, new iterative solution. Okay, what is the iterative solution? X1 of the first iteration, X11. You can see the updation going on here. What is the iterative method we will discuss, but I am giving you an overall idea coming ahead for you. So we will have X2 of 1, so on, Xn of first, like first step. Similarly, you go on again till the nth step. For the nth step, what it should be? X bar m is equal to X1 of, yes, fine, X2 of, similarly Xn of n. But a good question is, choice was not good. Maybe, because n is already reserved. Yes. So xk at the kth iteration, your solution vector is like this. Okay. But how will you know that it is a solution? The moment you will see that it is converging, how you will know that it is converging? You can compare with your previous vector. Compare with the previous vector. If it is going on to converge, then the previous vector and the next, isn't it? Fine. So therefore, like that, you can know that it is converging. Okay. So we'll see all this, but I told you how the method is going on. Here the iterate, what is this? But this is the sort of method we will follow to obtain the solution. Is everyone okay with this one? Hmm? Okay. So now I ask you, just look into this system of linear equation. From the first equation, can you give me what is x1? X1 equal to, from the first equation, x1 equals to, louder, common sense. So I told you, in this class, you just need some aptitude and basic common sense, nothing more. Okay, so how you will solve it? You have x1 over here. This is your gold you want to get. What you do? Transform every other part, all this, to the left hand side. Transfer everything to the left hand side and divide by. That's it. So why there is huge silence? You should prompt out. That's how it should not only me be talking. It should be you talking and me talking. That's how the energy will flow among us. Okay. So tell me how it is. X1 equal to 1 to x2 plus something till, yes, fine, okay with you, done, that's good. So divided by a11, okay with you, yes, okay. So now you wrote x1, can I ask you, in general, what is xi? What is xi? Xi, you know, x1, x2 up to xn. So I will go from 1 to n, isn't it? So in general, you told me about xi, x1. So I am asking you, just tell me about xi. Can you p I minus I2? Is it ai2? No? Is this correct? I plus 1. Then x I, okay. Then so on till sure, you have to make sure that in this process, you are not writing I also there. You are not writing I. And this xi is, you are taking it from the diagonal terms. You are taking from the diagonal. So A22 should not be there here on this right hand side. Yes. So therefore, you can continue so on till A2n xn divided by A22. Sorry, AII. Isn't it? Oh no, AIN, right? You tell me if I'm writing it correctly. You have to rectify this. Okay? Everyone agree? Can we write it in a more smooth way? Xi equals to Bi minus, can we do a summation? Okay. So what kind of summation shall we do? So go, you should tell him that, you see, if you are taking 2, 1 is also going there and greater than that is also going. So you have to take from I equals to 1 to n, but you have to tell him that, maybe, can we write in a good way? I is already used here. So j, let us use j. Let us use j. I index is already used. And you will say j is not equal to I. Fine. J is not equal to aj. Think. I will let you think about this a bit. Because this is one of the most, if you know about this, then everything will be fine for you. I feel that this is also not correct. Because why? Why I am telling that this is not correct? Because you can see you have written I comma I plus 1. But take an example of this. You have 2. Is this 3? No. So that you, how can you do this? Yes. So can we think of something new? Think about it. So should not hurry. Think properly. I gave them a new index J. Okay, not to confuse anything. Hmm? Yeah. Anyone? Last. Last. How about this? How about this? I will write it here for you. A I J. A I J. So here you can see that yes, 2 come and 2 comma n minus 1 can come. Okay. So there is no particular pattern. There is no particular pattern. I'll come take I. No, the fact is you are to see from the first equation, you took x1, okay, and you took all the elements right hand side to it on the left. But when you are trying to solve x2, then there are some elements on the right, but there is some element on the left as well. Yes. So therefore, there is, you cannot say I plus 1 pattern. Okay. So there is another pattern I minus 1 as well. Yes. So therefore, you cannot think where you cannot control them. So therefore, I told when you want to see about I, therefore I created an independent index J. Okay. So J is going from 1 to n, but I'm saying J is not equal to I. I'm saying J is not equal to Y. If J equals to I, what it means? X, but Xi is already on the left. So therefore, if you are writing xi here, I am claiming that you cannot have xi here. Okay, that's the idea. So aij times xj. How about that? Simple, simple enough. But I assure you that there is a pattern. You got a pattern, but there is another pattern I want you to see, and that pattern is see the second index, see this index, see this index, then this index. Can you see the pattern over here? And can you now motivate yourself that why I wrote a J here and then a J here? Everyone making sense about it? Getting idea, right? Any pattern you take, this second component is equal to the same. Even here, same. Isn't it? So aij into xj. So here the second component is j and second component is j, as usual with other guys. Last bench, okay, understood. Yeah. Okay, so you understood this one, fine. Okay, but is it enough? Is it enough? What we have to do more? Divided by a, divided by a. Yeah, but what should I write? What you should divide by? Ij, aij. What should I divide with? What should I divide with? What should I divide? Yeah, aij. Yeah. Okay, okay, fine. Now, everyone back on track. So now we have written a solution xi in terms of other variables. So we will be using this formula throughout for the two of the methods. Because we will use this formula only. Simple this formula. Okay. Divide by AI. Why it is the case? You want to know? Okay, why it is the case? See, I told you, the first equation you wrote, x1 you solved, isn't it? While solving x1, you did divided by a11. Yes, because that is the coefficient here. Now I ask you, can you write similarly x2? X2, but while solving for x2, I don't want you to solve for the first equation, rather use the second one. From this equation, solve x2. x2 equals to x2 equals to from this equation, second equation, what is x2? Take all these elements here on the right hand side. This element on the right, divide by a2. No, everyone write x2. Everyone write x2. x2. On your notebook, everyone write x2. What is x2? Second equation. Fine. Okay. Now, xi I wrote like this. Everyone is happy with this equation. Xi equals to bi minus summation aij xj divided by the aii term. And why we were dividing by xi term? We were taking from the diagonal. So if you want to solve a xn, we have to take this form. and you have to solve the last equation. Okay, so you got an idea of how this is working. Now I also told you that your numerical scheme is we start with an initial guess, that is x0, then apply an iterative method and again get x1 1, the first iterate, second iterate, so on till you converge. That's the idea. Now how can we use this? Okay. So just remind yourself, how about I write like this? Xik, that means the kth iteration value. Kth, Xik means at the kth iteration, what is the value of xi? Xi unknown. Yes, the kth value is equal to bi. Bi is not going to change, that is a constant, minus summation j equals to 1 to n, j not equals to I, fine, aij, xj at kth step, divided by also not going to change. Sorry, I did a mistake. This you already don't know, this one. Okay, so it should be your past. Can you see now? Can you see? Your future, that is the future kth iteration step. The value at the kth iteration is coming from the past step, k minus 1. X11, the first iteration step value was coming from the past, that is 0. That is 0. The 0th iteration was giving you the first iteration value. So therefore, same here, if you want to determine the kth iteration value, the past is going to help you, k minus 1th step. So you can see how this is coming here. Fine. But yet, this is not a numerical method. Yet, this is not a numerical method. What is a numerical method? If we replace this quantity, maybe I'll write it here in green. Then there will be just here, maybe here, maybe. There will be just an addition over here. aii xi of k minus 1 as well. To understand this, what I am doing here, in your first step, in the here, xi was not involved, right? Xi was not involved. Xi I have to involve. That is not involved. Everyone got the idea? Xi at the kth iteration, the past of that state, what is xi k minus 1 is not involved. So you have to involve it. That's how you make the numerical method. Okay. So this is a new addition for you to make a numerical method. If you do it, okay, if you do like that, then can you solve it efficiently more? So I can write this one as xik is equal to, see here, is this the coefficient aia? Yes, you are dividing by aia again. So they should cancel out. Okay with you? Should they cancel out? Here there is aia, here there is aia. Cancel out. So xi at k minus 1th step plus then remaining as per your step bi minus j not equal to I, okay, and aij xj k minus 1. Nothing else. Are you understand how many of you did not get? Did not get. Okay, so let me rub all this. Let me tell you again. Let me tell you again from the. It becomes a numerical method. It becomes this one we wrote, right? This one everyone understood. This one everyone understood, I hope. Okay. Now what I am telling is you are making it a numerical method. You are making it a numerical method if you are eliminating this guy. Just eliminating this guy. You are making a numerical method just by eliminating j not equal to y. That's it. Nothing else. If you do, yeah, let us go back again. Now you know it. So if you don't use j not equal to y, that means j equal to y can also go inside the summation. Yes. What will be the term? What we are eliminating? A, I, of course, X, J, Xj or Xi, whichever, Xi, K minus 1. Is the term, right? This is the term which we are eliminating here, J not equal to Y. Okay, so this is what you got from the equations. Above equations, you solved it. Now I am telling you that you are creating a numerical method. You are creating a numerical method if you write it like this. Xik equals to Bi minus just j equals to 1 to n Aij xj k minus 1 whole divided by Ai. What do you think? Can you see the difference between the two? What is the difference between the two? J not equal to y is not written. J not equal to y is not written over here. That means here already you are taking a new term apart from this. And what is that new term? A I x I k minus 1. That is being added now newly. Okay. Now why it is being added? It might seem like something like we are doing artificially. Why it is being added? It has a purpose. It has a purpose. What purpose it has? The purpose it has is, suppose it went inside that summation. It went inside that summation. Then you have AIA here and you're dividing by, fine, fine. They will get cancelled, isn't it? How then this one, how it will look? Xi at the kth step is equal to Xi at k minus 1 step. It will come out, right? Come out of the summation. Yes, plus this whole term will be there again. Bi minus summation j equals to 1 to n Aij xj k minus 1 divided by Aii. But since you have already taken out this term outside of the summation, so j not equal to I has to be written. Otherwise, you are adding it again. Are you getting it? Fine. Now it is fine with you. So unintentionally, we are doing something new. So to this equation which you had already, we are just adding the past state, past value of k minus 1th iteration. If you want to compute something at the kth iteration, this is all what we are doing. In numerical methods, you should remind yourself that the future iterate depends on the past iterate. The future iterate value only you can compute. How many of you did not understand it? So then you have to, this is just the way I'm telling you how to approach this. Otherwise, you can think of this as something else. You can as xi at the kth iteration is equal to xi value at the past iteration k minus 1th plus some correction. Some correction. What is that correction? The correction is equal to the same. Here correction we usually write as Ri, that is residual, something like R residual, Ri, and that Ri is equal to just the same which you have written down, Bi minus summation Aij x j at k minus 1th divided by Aii, j is running from 1 to n, j not equal to I, because he already took the ith outside. Fine with you? This is just the numerical method for this. And this method is known as the Jacobi method. Now you can solve each of the unknowns in the same way. Each of the unknowns in the same way. Okay. Fine. Now Guys, I want you to understand carefully. Use your mind properly. Use a bit of visualization in your thinking now. What I'm going to say. What I'm going to say. So you wrote this equation, isn't it? So I'm asking you, while solving, think that you are now solving x1, x2, x3, xn. You are solving in your notebook. Think in that way. You are in that zone. So that is the first unknown. Now we go to the second unknown. When you are solving the second unknown, you are using all of this, right? All of these other variables. Yes. When you are solving for x2, still when you are solving for x2 at the kth iteration, you are using the past iteration of all these variables. Fine. x2, x3, x4, x5, so on. But the most important thing is you are also using the past value of x1. You are also using the past value of x1. But that is inefficient. Why? Because in the previous step, you computed x1 at the kth iteration, but you are using x1 at the k minus 1. Are you getting the trick here? How many of you are not getting? Okay, slowly you will get. Slowly you will get. Okay, what I am telling you is, you solved x1, right? Let me write this. Let me write this so you will understand. Let us come again. Solving the first unknown. Solving first unknown. That is x1. You are solving x1 at the kth iteration. Then that is how you are getting. That is you are getting as some combination of the past. That is past xi of k minus 1th terms. Everyone happy with this? Yes. You are getting x1 as some combination of the past xi k minus 1th terms. Right? Now let us come to x2 at the kth iteration. What will be? x2k will be combination again of past xi k minus 1 terms. Again, I going from 1 to here also I is going from 1, 2, 3. Step. After this second step onwards, if you do like this, you will get solution. I am not saying that you will not get to the solution. You will get to the solution, but it is inefficient. Why it is inefficient? I am asking you. There is just a tiny visualization is. Do you think I am writing it is a combination? Let me write. It's a combination of, can you tell me, x1 of k minus 1, x2 of k minus 1, x3 of k minus 1, so on. xn of k minus 1. Agree, everyone? Everyone agreeing it? Everyone agree? It all is a linear combination of this. Yes. Solve the new value here, x1k, but still in your method, you are using the past value of x1 k minus 1. Why not use this updated one here? Right? Instead of x1 k minus 1, you can use x1 of k, which is the fresh x1 state. In that way, the method will be more improved. Mr. Black, you're getting bored, is it? Huh? Are you understanding? So are you getting... So wait. Yes. So you can see the problem here. You can see the problem here. I'll come to it. We see the problem we saw is x1k you solved as the combination of past states. Fine. When you encounter x2k, then you see that we are also using x1 of k minus 1. But in the previous step only, you calculated the fresh future state of x1. Why can't you use it and make the iteration more better? That was our concept. Now, if you see the further values x3k, then x3k according to this rule will be a combination of x1 k minus 1, x2 k minus 1, x3 k minus 1, x4 of k minus 1, so on till xn of k minus 1. Fine. But again, we have the same trouble here. That why are we not x1k and the previously computed x2k? Here, it will be much better. Okay. So now, therefore, we are learning a new method after Jacobi. Okay. Jacobi is not doing it. Jacobi is always taking the past values. But to improve this technique, to improve the Jacobi technique, Jacobi saw that like Gauss and Seidel, they saw about this, that Jacobi was using the past, even if the future state was state. Okay, he was not eating the fresh curry. Instead, he was going to the 1 day old curry. Okay, so he thought, why not I go to the fresh curry? So he started using the fresh values, and that's how he made a efficient method. Then Jacobi. Okay, so if Jacobi method we are going to write, if we are going to write the Jacobi method, intuitively think that this guy will change. The correction term will change, isn't it? How the correction term will change? Some of the terms before 3, x3. If you are computing x3, then all the terms before that, x1 and x2, those will have the fresh values. Then let us keep the past values because we don't know the value. So x1 and x2, that is before x3, will have the fresh value, but after x3, that is x4, x5, x6, and so on, let it be the past values because that is not yet computed. Another step to compute. Got that? So Gauss Seidel method will have some combination of fresh values and some combination of past values. Everyone agrees with this? Now, can you see that this equation will change accordingly? This equation will keep the same equation, but it will change accordingly. Can you tell me, like I told you, what is the idea? Can you just tell me how the summation, this equation Gauss Seidel? Think about it. Let us begin. Let us just use your common sense and visualize this. Xik, again we will compute xik, that is equal to the past value of xi at k minus 1, fine, plus a correction term again a new correction term ri. Now your aim, ri should be bi, that is not going to change. Is that going to change? No, that is a constant vector. That is a constant vector, so it is not going to change. Bi is same. Then minus some summation divided by aii will change? No, that will still the same. The summation part will change. Anything summation part. Now, please think how the summation part will change. Just you have to write it according. So I told you, just visualize this example before. When you took x2, what fresh value are you using on the right hand side? What fresh value are you using? Understood. What fresh value are we using? See, for x2k, right? You are solving this one, I'm telling you. This one, you are using x1, the fresh value of x1, right? x1k. When you are using x3, you are using x1 and x2 as the fresh value. So I'm asking you that if you are using xik, then all values less than I will have the fresh value. all values less than I will have the fresh value, isn't it? Because those are the terms you already computed. So therefore, that will have a summation j equals to 1 to I minus 1 till I minus 1. What you have? Aij, xj, k. Because that's the fresh value. That's the fresh value. Plus. Sorry, minus. Still minus is going on, is it? Minus summation j equals to till I minus 1 you have already kept in your box. You have to go till, so the summation would go from j equal to I to n. Yes. And then what you do, aij? Huh? I plus 1. Oh, yes. So, yeah, good. Good observation. So, I plus 1 to this at k minus 1. Can you see what is happening here? So what is happening here? So I wrote this summation which you saw before as I have broken it down to two different summations. One here is the fresh values are the past. Okay. If you are using Jacobi method, okay. So what is your iterative scheme before starting out? What scheme are you going to follow? So x1 of k, that is the future, it is depending on the past. So from the first equation, can you tell me what is x1? First equation, tell me x1. 7 minus x2, wrong. Sorry. Why it is wrong? You are not computing x1. You are computing x1 at the kth iteration. So x1 at the kth iteration should be equal to 11 minus x2. It's just not x2. Divided by. Now, mistake. Don't feel down. Okay, like this Bhavya. Okay, sorry, Kavya. Don't feel down. Okay, by doing wrong thing only you will progress. Learn. Then x2 at the kth iteration is equal to, tell me, 11 minus x1 at, I told you, the Jacobi method prefers old curries. So old curry is this one, k minus 1 is by 10. Fine? Fine? What shall we do now? Can you start with any initial condition? Now actually you solve it, no, yeah, maybe solve it by hand. Solve it by hand. Just by hand, what values are you getting? x1 equals to, x2 equals to, 10 is there, 1 is there. So how it can make out to 11? Just add them 1, 1. Okay, so the solution will be 1 and 1 just by looking into it. Now we are understanding if Gauss Seidel and Gauss Jacobi method will actually give you this. Okay, all right. So what I ask you is here, starting guess, initial guess. Let us you start with initial guess. x1 0 and x2 0 as Then can you tell me, based on this iterative scheme, based on the iterative scheme, what is x1 of 1 and what is x2 of 1? Hmm? Got idea now, right? Then you can compute x2 of, sorry, x1 of 2, then x2 of 2, similarly x2 of 3. So yeah, okay. So you can see the first iteration, even if you started from a very far value, that is 0.5 and 0.5, you already know the solution as 1, 1. Okay. Started from 0.5 and 0.5. By the second iteration onwards, you converged almost solution, but still it is not equal to the solution. It is a bit far. Okay. Therefore, when you did the second iteration, coming very close to your solution, 0.995. What is the difference? Of order 0.005. This is the error. Yes, because if you add 0.005, you are getting 1, right? To the true solution. So you know the error is 0.005. Now, when you did 1.0005, the next iteration, what is the error here? 0.0005. So you can see the error is keep on decreasing, and at the same time, you even converge to the solution nicer way. Okay. Now, this is the Gauss Seidel. Maybe we can stop here. Sorry, this is the Jacobi method and stop at the Jacobi method. Okay. Now, do you think shall we continue with the Gauss Seidel and after that it is a break? Just you to know that how it is. Otherwise, there will be a break in what you are doing it. Okay. So let us go to Gauss Seidel. Keep the Jacobi as it is. What is the iterative scheme for the Gauss Seidel? Remember, Gauss Seidel likes fresh curries. Okay. So therefore, everything fresh you will keep. So how you will keep everything fresh? So x1 of k is equal to 11 minus x2 of k minus 1 as usual. Why? Because you don't know x2, the fresh value of x2, because you are computing x1. Okay. Now x2 at k step is equal to 11. Tell me. Yeah. Anyone else? Last. There. What should I write here? K. Yes. K. Because x1 k is already computed. That's the fresh. So wherever possible, write the fresh values. Divided by 10. All of you got this idea of using the fresh values. On the first state, we did not use fresh. Why? Because x2 at the fresh value, we don't know. Because it is not yet computed. x2 at kth value involves x1. So we are using the fresh value of x1. Already computed in the previous. Now, suppose initial guess. For x1 of 0 is 0.5 and 0.5. Can you tell me what is x1 of 1? What is x2 of 1? That is the first iteration. X1 of 2, x2 of 2. Maybe the third iteration. X1 of 3, x2 of 3. Can you tell me this? Now can you appreciate? Now can you appreciate the two methods? Which one is better? Gauss Seidel, and the picture is right in front of you. Okay, just by this simple equation we showed. So you can think what Gauss Seidel can do for complicated equations, like a large number of equations, large number of methods. Moreover, you can see in the in the second iteration itself, error of the order of 10 to the minus 5 as compared to the third step of Jacobi. So you can see how Gauss Seidel method is highly improving and efficiency of your roots, of your solutions. Okay. So I hope you can appreciate through this example. So you can appreciate that by using the fresh value, by using just the fresh value, which is x1k here, you improved your accuracy. That's the idea. So you can see the difference. Even in the first step, the 1.05, 1. All the x and y are the same. X1, x2 are the same in the Jacobi method. Whereas in Gauss Seidel, due to that difference, every term was getting new. That the first and second components were different. And moreover, they are converging in a fast way. It is having accelerated convergence. Fine. Okay, so after the break, we can discuss more about this.